honor for me to show my work to a continual learning community. I am a PhD student enrolled in CISA in Trieste, in the Department of Data Science. I will present my work about direct feedback alignment applied to continual learning. My supervisor is Sebastian Gold, and Biplov Arora is also helping me out. Okay. So what is direct feedback alignment? I think most of you have never heard about this. It's an optimization algorithm alternative for backpropagation. The main idea is that it works in two phases. In the first phase, there is an alignment phase. Also, in the name direct feedback alignment, it's present this feature. So in the alignment phase, even if the method starts from a different initialization points, the weights move towards all the same direction. So there is an implicit bias in this algorithm. And we already know that in continual learning, an explicit bias introduced to the laws, like for example in elastic weight consolidation, has been shown to be successful in continual learning. So we were wondering if this algorithm that has the bias intrinsically in the update rule could be helpful. So why is this alignment happening? So on the left, we see, for example, a representation of a three-layer neural network with BP. We see that the forward pass goes through the feedback, the weight matrices. Instead, the backward pass goes through the weight matrices transposed. In DFA, the error is mapped directly to each layer, and the derivative of the following layers is not considered in the update rule of the early layers. Here, don't be scared. I just want to compare the equations of BP and DFA. The last layer is updated exactly in the same way. The error is mapped in the same way. In W2, the matrix of the intermediate layer has this difference instead. Instead of W3 transposed, we have B2. So it's intuitive to think, to understand that the weights of the last layer will have to align to the W3 transposed to really have the gradient. So in order to be able to update the loss according to the learning that it needs. For the update of the first layer instead, B1 is a proxy of W2 transposed and the derivative of the following layer. So B1, the weights of this layer will need to align to a bit of a more complex object, but still defined and depending only on the feedback matrix. The feedback matrix is initialized as a uniform random distribution and is kept fixed along through all the training. We can see later that we can change this feedback matrix for the different tasks in continual learning, or we can keep it in the fixed as well. Here is another representation of the alignment, and here they say memorize, but it's actually meaning learning the data set. So from an initial point of view, first the weight will align to the values of a feedback vector. Then among all the possible solutions of the weights, the solution that is selected is the one with the same gradient as the feedback vector. For example, here it's a small example. We have two positive numbers and one negative in the middle. So the solution that will be selected will be the one that has the weights with the same gradient of the feedback matrix. I hope this is clear. So what are the advantages of DFA? We already mentioned the implicit bias. We will try to exploit this bias for continual learning. The fact that the weights are not the same for the backward and the forward pass makes this algorithm more biologically plausible. In fact, was born in 2016 as a biologically plausible algorithm. And the train of the different layers can now happen in parallel. which goes in the direction of a saving of energy, which continual learning method should keep always into account. And then has other technical advantages. For example, the activation function can be non-differentiable because we don't need anymore to differentiate for that. That said, in the literature, studies about the scalability of biologically plausible algorithms have placed DFA in disadvantage compared to BP. But this is only regarding the test error, so the error on the data set taking consideration. We will see that in the continual learning context, this can be reversed. This was an example on NIST and Cypher-10 of fully connected, and we can see that the error was always larger than BP for the DFA method. The dataset that we will use are the split and the permuted fashion MNIST. We also tested the same things on split and permuted MNIST, and the results are the same. I'm sure most of you will already know this benchmark, but I want to stress that if I apply different similarity measures to the images of the same class among the different tasks, for example, CKA is a measure that is orthogonal invariant. So is one when the two images are only rotated, which is the case of the permuted dataset, and is zero when a rotation doesn't match the two images. CCA is a measure which is linearly invariant, so also allows rescaling. So applying different similarity measure, we can see by eye that the permuted dataset is much more similar among the tasks. Instead, the split dataset has tasks more uncorrelated with each other. We will apply, in this context, DFA with the same feedback metrics and DFA with the different feedback matrices in order to test if the alignment, the implicit bias needs to be the same throughout the tasks, or if what we find is only a matter of chance. We will see that actually learning in different, with the different feedback metrics, so pulling the weights in different direction will be actually beneficial in the most uncorrelated data set. I will show the results with this kind of plot. I will put the backward transfer on the x-axis. So if we are on the higher part, we have zero forgetting, and instead I will put the average test accuracy on x-axis. So if we will be on the right, we will have 100% accuracy, and we want to place ourselves in the right upper corner, where the method will have zero forgetting and 100% accuracy. I'm sure most of you know the definition of these two measures. So our first baseline is a random feature model, because DFA can actually risk to approach a random feature model when the feedback metrics become, the variance of the feedback metrics become very small. We actually find that the variance of the feedback metrics is the parameter that can tune DFA along the plasticity stability trade-off. DFA can reach zero forgetting or can reach 100% accuracy with minus 40 point inaccuracy of forgetting. This depending on the variance of the feedback metrics. As I said before, as the variance is smaller and smaller, B, which is the feedback metrics, will have smaller entries that approach zero. That makes the update rule have a smaller update, because B is directly multiplying the learning rate. So these are the results on the split and task incremental learning. I also put a comparison of BP, which is in the green dots, with two kinds of learning rates, to show that also for backpropagation, the learning rate is the parameter that tune the method along the plasticity stability trade-off. In the permuted dataset instead, DFA has a larger gap to random features. It's more or less 10 point inaccuracy. Instead, before it was only 1 or 2 point inaccuracy. That said, what happens if we change the feedback metrics along the different data sets? So the blue line is the case where the feedback matrix is reinitialized for the beginning of new tasks. So the weights are pulled in different directions. And as I mentioned before, there is only a loss in 5% accuracy and still being able to reach 100% accuracy for DFA with different feedback matrices. So this was surprising at the beginning, but then we actually understood that that of course changing the direction of the bias can be beneficial for uncorrelated datasets. This is also the case of elastic weight consolidation, which is the red dot. These are the results for the task incremental learning, in which the last layer is reinitialized for every new task, and it's specific for every task. But what happens in the domain incremental learning is that where the whole network is shared among the tasks, including the last layer. So below, I show the plot for this scenario. And now the trend is reversed. The FA with the same feedback metrics is more powerful either in the split and in the permuted dataset. And the reason for this is that probably reinitializing the output layer, the gradients needed more time to reach the convergence with the feedback metrics. Instead, keeping the whole network the same and the feedback metrics the same, we can have 100% accuracy. In this case, we cannot reach a 0% forgetting, but it's because it's the domain incremental learning. Also in the permuted dataset, in the domain incremental, the performances reach up to -20. The random feature is not anymore available in domain incremental learning because it is based on the fact that the output layer is specific. And in this case, the output layer must be shared. So the summary of my results are that the FA show in the context of continual learning better performance in the backpropagation. We found that the variance of the feedback matrix is the parameter that can fine-tune the FA along the stability plasticity trade-off. And we show that with changing the feedback matrix for different tasks, it can be actually beneficial. For example, in the task incremental learning scenario for the split dataset. Future direction will be, first of all, increasing the size of the network and see if with more and more layers at zero forgetting, we can have larger accuracy. Then, second of all, we are planning to apply the same similarity measure we apply to the datasets to the representations of the network in the intermediate layers. To see, for example, if representations in the DFA same are kept more similar with respect to the representation in DFA diff. A bit of a further direction will be apply DFA to reinforcement learning and continual learning, because there are, for some games, already multi-layer perceptron that work, and we are working with fully connected networks. But in this case, backpropagation is more in difficulty. So we will see how DFA will place in that case. Last but not least, applying and introducing further biologically plausible features. I'm looking forward to hear the dendrite talk at the end of the of the conference, and yeah, we can borrow more biological plausible ideas to the update rule. So thank you very much for your attention, and please, your feedback is welcome either now or this is my email. Okay, thank you very much.
Great, thanks for that great presentation.